Another thing that the second derivative can do for us, besides indicating the intervals of concavity and then using that information to find the points of inflection, another thing it can do for us is actually determine whether we have a minimum or a maximum at a specific point. And that's what we're going to call the second derivative test. I know it's weird. The first derivative sign chart and the interpretation of it to find maxes and mins, that's what's called the first derivative test. The second derivative sign chart process, which we learned in the last video, that's very useful, and that's how you find your intervals of concavity and how you classify your points of inflection. But that is not called the second derivative test. The second derivative test is another way to find minimums and maximums using the second derivative. It has nothing to do with a sign chart. So I know it's a little bit weird. I wish the second derivative sign chart was called the second derivative test, but it's not. But here is the second derivative test. There's another way to find minimums and maximums. Let's read it. If the first derivative at a point is 0, and the second derivative at that same point is positive, then let's see what type of extrema we're going to have. If the second derivative is positive, that means concave up. Okay, now, if all you knew was concave up, you'd be stuck, because every single one of these infinitely many points, the graph is concave up. Only one of them is an extrema, and particularly is going to be a minimum. And it's the one right here at the bottom, the one that has the horizontal tangent. So you got to have both conditions. Just having this is not enough. Just having this is not enough. This means it's a critical point. It's worthy of further investigation. And then you can see what's the concavity at that critical point to justify it as either a min or a max. But if your first derivative is 0, that means it's a critical point. It's got the horizontal tangent. And at the same time, the graph is curving upwards. We know that point is going to be a relative minimum. Okay, now vice versa. If the first derivative is 0 and the second derivative is negative, negative means concave down. And then if you have a horizontal tangent when the graph is concave down, we know the combination of those two facts is going to be enough for us to conclude logically that we're going to have a relative maximum. Okay, so be careful. Negative did not mean minimum. The negative second derivative meant concave down, and then if it was concave down and you had the horizontal tangent, that would mean a relative max. Positive didn't mean max. Positive meant concave up, and then concave up meant that point at the bottom with the horizontal tangent was a minimum. So your second derivative test is a way to just be very specific and very targeted with how you can find mins and maxes. You don't have to do a whole sign chart, so you don't get all that work done. It's more specific. You just plug in to the first derivative, and you need to confirm that the first derivative is 0, and then you plug that number into the second derivative, and then that result had better not be 0. If the second derivative does equal 0 also, then the second derivative test fails. It's inconclusive, and you would need to do the first derivative test. You need to do the sign chart to figure out if it's a min or a max. So we check to see if it's a critical point. First derivative has got to be 0, and then I check the second derivative to see what type of a critical point. If it's concave up, that means the point has to be a min. If the graph is concave down, the point has to be a max. And another note, if your first derivative is undefined, that means you have a critical point, right? If your first derivative is undefined, that's a critical point. But if your first derivative is undefined, your second derivative is also undefined, right? And so there would be another case when the second derivative test is not useful, right? You would have to do the first derivative sign chart for any of these critical points that are undefined. So these only work for the nicest critical points, the ones where the first derivative is 0, and then you can just plug into the second derivative, see whether it's concave up or concave down, and then that'll tell you whether it's a min or a max. Okay, let's practice. Given this function, use the second derivative test to figure out whether I have a local max or local min at -3, and then justify my answer. Okay, so the first thing I need to check is the first derivative equal to 0? Well, let's go get the first derivative. It would be 2x squared plus x minus 15. And I don't have to factor that. I could if I wanted to, and I could do a sign chart, but you don't need to. All I have to do is take this first derivative and then plug in the one value that I'm investigating. So let's see, 2 negative 3 squared would be 9, minus 3 minus 15. So that's 18 minus 18. Oh, look at that. If I plug in negative 3 into my first derivative, I get out 0. That's important, right? It is a critical point. That means it's worthy of further investigation. So now I need to take the second derivative and see what happens. Second derivative would be 4x plus 1. I don't have to do a sign chart. I'm just going to take that second derivative and I'm just going to plug in the value that I am investigating. So let's see, that's going to be negative 12 plus 1. So my first derivative was 0. That means it was a critical point. That means I need to do some more investigation. Then when I plug that same x value into my second derivative, I get a negative result. Negative means concave down. And if the graph has a horizontal tangent and it's concave down, I could say f has relative max at x equals negative 3 by second derivative test. Okay, and then your justification is your second derivative test. Or you could say, because f prime equals 0 and your second derivative was less than 0. But again, you don't have to write this if you cite the test. If you cite the test, you don't have to tell me what the test says. But if you don't do this, then you would need to write something else. But if you've got the work shown, you're probably going to be pretty okay. The other critical point, I believe, for this one would be a negative or a positive 5/2. So let's check it. This one only asked for negative 3, but if it wanted to test 5/2, we could also. If I plugged in 5/2 into the first derivative, let's see, we'd have 2 5/2 squared plus 5/2 minus 15. So that would be 25 over 4, so then 25 over 2, plus 5/2 minus 30/2. So that's 30/2 minus 30/2. So there you go. The first derivative is 0. So that means that is a critical point. And then you could test it with the second derivative. 4 times 5/2 plus 1. So that's going to be 10 plus 1. That's 11, which is greater than 0, which means concave up. So I could say f has relative minimum at the 5/2 value. And again, you could cite it by saying by second derivative test. Now, all this stuff about the 5/2, that was extra, right? That was just to show you that this function, it did have 2 critical points. It only asked me about the 1, so you only really needed to do the 1. But if it asked me about the other one, I could have just as easily had done the other one. And notice there are 0 sign charts involved, right? There are ways to do it with a sign chart, but that's not really the way that the AP exam wants you to do it. Okay, so next example. Give this function, use the second derivative test to figure out whether we have a max or min at pi over 6. Okay, very good. First thing is let's go take the first derivative. The derivative of a negative 2 cosine would be a positive 2 sine. And the derivative of negative x would be negative 1. Then I'm going to take this value and test it, and I need the first derivative to be 0. So I've got 2 sine pi over 6 minus 1. Pi over 6 is this point on your unit circle, which goes over a lot, up a little, so the sine would be 1/2. Ooh, so look at that. That's 1 minus 1. So the first derivative is 0. That means it's worthy of further investigation. That means it is a critical point. That's good. If the first derivative is any other number, right, if it's a 1, or if it's a 2, or if it's a 1/2, or if it's a root 3 over 2, if this is any number besides 0, you would say, I'm done. It's neither a max nor a min. If the first derivative is not 0, then your point is not a critical point, and it cannot possibly be a min or a max. First derivative must be 0. Okay, so now let's check. What's the second derivative? The derivative of a 2 sine would be 2 cosine. And then if I were to plug in my value, 2 times the cosine of pi over 6. Cosine of pi over 6 is your root 3 over 2. So I get the root of 3, which is positive. And if your second derivative is positive, that means concave up. And if your graph has a horizontal tangent, if the first derivative is 0, and the graph is concave up, you could say, therefore, f has relative minimum at x equals pi over 6 by second derivative test. So you check with the first derivative, and it needs to be 0. If it's not, you're done. It's neither. If the first derivative is 0, then you check your second derivative, and then it had better not be 0. Because if the second derivative is 0, then it's indeterminate. You can't really know if it's a max or min. You'd have to do the sign chart first derivative test process. Okay, 3 more examples on the next page, and then we'll be donesies with this video, and almost with this notes packet. Use the second derivative test if possible. Spoiler alert, it's going to be possible to find the relative extrema. So what's different about this example as compared to the previous 2 is that it doesn't hand me the x values for free on a silver platter. I have to find them myself. That's okay. A little bit of extra algebra, that's okay. First thing is to take the derivative, smelling like a 6x squared plus a 6x minus 12. So I have to find the critical points myself, so let's factor it. So let's see, I think that's a plus 2 minus 1. So then your critical points are negative 2 and a positive 1. Okay, you don't have to go plug these back in. They're going to be 0 because that's how we found them, right? By setting that derivative equal to 0 and then solving. So you don't have to check and make sure that when I plug this in to the first derivative, it's 0. It's going to be. That's how we found those numbers. So next thing, let's go take this second derivative. Let's come back up here. You'd have a 12x plus 6. And then we'll take these 2 critical points, plug them in, see what happens. So the second derivative, when I plug in negative 2, and the second derivative when I plug in 1. Let's see, so that would be a negative 24 plus 6. That would be a negative 18. You don't care about the 18, only that it's negative. Negative means concave down, which is going to mean max. And if I plug in 1, 12 plus 6, that's the positive 18. You don't care about the 18, just that it's positive. Positive second derivative means concave down, which means minimum. Okay, so here we go. Let's write the answers. F has relative max at x equals negative 2 and relative minimum at x equals 1 by second derivative test. And then all of this work, specifically this chain and logic, that's your justification. So that one was a little bit different because it didn't hand me the critical point, the test value, for free. You had to find it, but that's okay. All right, these next 2 are harder, so let's just try our best. Here it gives me an equation for f prime. It says f prime is g times x squared minus x minus 6. Then it tells me some pieces of information about g. It says g of 3 equals negative 2, g prime of 3 equals 7. Determine whether f has a max, a min, or neither at 3. Okay, so this one's weird because you don't even know what the f function is. You don't know what the g function is. It just kind of gives you the seemingly random pieces of information and then is asking you to answer a question, right? Seems weird. Let's start it, right? We know if we're trying to figure out if we have a max or min or neither, there's 3 tests that you could do. There's candidate's test, but we really only use candidate's test to find absolute extrema. So that one's off the table, right? That's a way to find max and mins, but we use candidate's test to find the absolute max and mins. To find the relative extrema, we either do the first derivative test or we do the second derivative test. Now the first derivative test is going to involve making that sign chart, testing all the critical points and the intervals between the critical points, and then you have to see, oh, okay, if it changes from increasing to decreasing, that's a max, or if it changes from decreasing to increasing, that's a min. You have to know a lot about the function in order to do that first derivative sign chart. In order to do the second derivative test, you only need a much narrower set of information. You only need to know what's happening at these specific points. So for this question, it doesn't specifically tell me what test to do. On the previous examples, it said use second derivative test. And if it tells you to use a specific test, you need to make sure you do that specific test. Here, it doesn't really dictate which one to do, but we're going to have to do the second derivative test. A, candidate test is wrong because we're not trying to do absolute. And B, I just don't have enough information to do the sign chart that would be necessary for the first derivative test. So the second derivative test is the only option I have because I don't have enough information for the other one. So let's check. If I want to see if f has a max, a min, or neither, first thing I need to check is f prime of 3 equal to 0. Because if it's not a critical point, the answer is neither, and we're done. Okay, so let's try it. We have this equation for f prime. Let's just plug in 3 and see what we get. It would be g of 3, and then you'd have 3 squared minus 3 minus 6. Okay, so let's see what we got. G of 3, the question told me, is negative 2. And then 3 squared is 9. 9 minus 3 minus 6. That's 9 minus 9. Ooh, that's 0. Look at that. Negative 2 times 0. That's 0. So the first derivative is 0. So we know it's not going to be neither. If this number would have been anything else besides 0, we would be done. We'd circle neither and we'd move on. But since the first derivative was 0, I need to do further investigation. I need to figure out what's the second derivative. Then I'm going to take 3 and plug it into that second derivative. Okay, well, let's think. If it gives me f prime, how do I get to f double prime? Well, you would need to take the derivative, right? That's how you get from the first to the second derivative. Now here I have g times this chunk, so you're going to need to use product rule, but that's okay. We know how to do product rule, so let's go for it. I need the derivative of the first times the second plus the derivative of the second times the first. So it's weird, but we could take that derivative. It's just product rule. And then I need to plug in 3 into this second derivative. So I'd have g prime of 3, 3 squared minus 3 minus 6, plus 2 times 3 is 6, g prime of 3. Okay, g prime of 3, the question told me was 7. Does it matter? Nope, because all this chunk is going to be 0, right? And that doesn't matter. Then we have this next piece. So we have 5, and then the g prime of 3. No, sorry. I don't know why I put this prime. That shouldn't be there, right? It was just g of x, so that should have just been g of 3. Sorry. So then the g of 3, let's go back and plug it in, was the negative 2. So then I've got f double prime of 3. That's going to be equal to negative 10, which is less than 0. And if the second derivative is negative, that means concave down. And if the first derivative is 0, and the second derivative is less than 0, which means concave down, I could say, therefore, f has relative maximum at x equals 3, and your justification is by second derivative test. So we wouldn't have had enough information to do that first derivative sign chart. We couldn't have done the first derivative test, but we could do the second derivative test because it's more focused, it's more specialized, it's more targeted. And so sometimes that second derivative test is the only option you have. Right? And that one was tricky. Hopefully it makes sense. You'll see stuff like it in the future. Like right now, the next example is going to be pretty similar, except slightly harder. Okay, so once again, suppose that we have some function and it's continuous. It's got a second derivative. Okay, wonderful. It gives me some list of information. It says f, f prime, and f double prime all being evaluated at 3. I don't know the f function. I just know this targeted information about x equals 3. Then it says let g be a function defined by g prime. And then it's asking me, does g have a local max, a local min, or neither? Okay, so again, second derivative test is the only way. First thing, let's plug in 3 and we'll check, does that equal 0? Because if not, it would be a short question. But this one really isn't max, min, or neither, right? This one just says, is it a max or is it a min? This one shouldn't be neither, but let's check it. Plug in 3 into this first derivative. Okay, so x squared minus 9, and then 2f of x plus 5f prime of x. Like, really don't even care. Did I know what f of 3 was? Yes. Did I know what this was? Yes. Does it matter? No, because all of this, right, all of that's going to be 0. So it doesn't even matter what that stuff is. The first derivative is going to be 0. And it had better have been, because neither was not an option. It says, does it have a max or does it have a min? It wasn't max, min, or neither. So I really should have gotten 0. And if I didn't, something would be very wrong. I'm going to erase this line just so I have a little bit more room. But yes, the first derivative must be 0. And then the second derivative must not be 0. But let's go take the derivative and see if we can finish this question. Again, product rule, derivative of the first times the second, so it's 2 f of x plus 5 f prime of x. So the derivative of the first times the second, plus I need the derivative of the second times the first. I'm just going to copy this first. So derivative of the first times the second, plus I still need to do the derivative of the second times the first, but I just copied. Okay, now let's go do the derivative of the second piece. If I had 2f plus 5f prime, just add an apostrophe to each one. That'd be 2f prime plus 5f double prime. So the derivative of the first times the second, plus there's the derivative of the second times the first, and now I need to take the second derivative, and now I need to evaluate it at the point that I'm investigating, which is 3. 2 times 3 is 6. Then I have 2, and then let's see, f of 3. Let's go get f of 3. F of 3, it told me, was negative 4 plus 5. And then let's go get f prime of 3. F prime of 3 was 1. And then plus, let's see, 3 squared minus 9. So 3 squared is 9. So that's all 0. Did I know what f prime of 3 was? Yes. Did I know what the second derivative at 3 was? Yes. Does it matter? No, because all that's going to be 0 because of this piece, right? So that's really nice. Let's finish it. Got 6. That's negative 8 plus 5. 6 times negative 3, which is negative 18. Which is negative. Therefore, the graph is going to be concave down. And if the graph is concave down, I could conclude, therefore, G has relative maximum at x equals 3 by second derivative test. Okay, so those ones are a little tricky. Hopefully it makes sense. Second derivative test has nothing to do with intervals of concavity, has nothing to do with points of inflection, has nothing to do with that second derivative sign chart. I know it's weird because the first derivative sign chart process, that culminates with your first derivative test. Just remember, your first derivative test, that's a way to find mins and maxes. The second derivative test is another way to find mins and maxes. But you don't do that by using the second derivative sign chart. The second derivative sign chart gives you intervals of concavity, and that gives you points of inflection. If you want to test for mins and maxes using the second derivative, all you have to do is plug into the first, make sure it's 0, and then you plug into the second, and then make sure it's not 0. If it's a negative output, that's actually going to tell you a relative max. If it would have been a positive output, then that would have told me we had a relative min. Right, so a second derivative test, no sign charts involved, but it's a way to find mins and maxes using the second derivative.